Hello everyone. This video will share insights about our final mechanical engineering project, the Maze Runner, including its goals, processes, and results. The project aims for our robot to start at the start of the maze and navigate autonomously, eventually reaching the exit. While designing, we had 5 main goals. First, we wanted to avoid any unnecessary movements. We wanted our robot to be as small and lightweight as possible. It was important to avoid any collisions with the walls to protect the maze's integrity. Ideally, we wanted a short completion time. Our design process consists of 4 steps, about which we will provide more detailed information afterwards: CAD design, algorithm development, closed-loop control system, and testing. These steps were not in order during the project, but intertwined throughout the whole process.
Our microcontroller was Arduino Uno. Our chassis was designed and 3D printed in Makerspace. For joints, we used bolts and plastic clamps. We had 3 wheels, 2 of which were powered wheels, and the other was a caster wheel. We used the 3 ultrasonic sensors and 1 gyroscope to understand the distances and directions. We used 2 lithium-ion batteries to provide proper current and sufficient voltage. Finally, we used several control systems values to obtain more precise movements. The constants of this control system were obtained from trial and error. In this slide, you can see Fusion 360 image of our final robot on the left and our real-life assembled robot with ultrasonic sensors and our handmade PCB implemented on the right. Here we can see our handmade Arduino Shield PCB. We wanted to create it so that our robot would use minimal cables and have a compact design.
As we have mentioned before, we are using a closed-loop control system to move efficiently and protect maze integrity by minimizing collisions. So we have 2 main controllers, a gyro and an ultrasonic controller. During straight movements within walls, the gyro PD controller does not have much impact, but when there are no walls, its impact is much higher. Likewise, just the opposite scenario is valid for the ultrasonic PD controller. In turn, only a gyro controller is used, and it is a PID controller with a conditional line. We are going to explain the conditional parts later. The ultrasonic controller allows the robot to stay in the middle of the 2 walls while moving forwards, trying to keep the distances between the left and right walls equal. The base speed while moving forward is 130 RPM. So in order to make the adjustment to force the robot to the middle, the controller adds an extra speed or subtracts for each motor. The gyro controller aims the robot to turn 90 or 180 degrees in turns, if needed, to keep the initial orientation stable so that the robot can remain still even without being between the walls. During the turning, there is a PID controller with a conditional integration coefficient. The reason for the conditional integration is that there is no base speed while turning, like the ultrasonic controller. The power comes from the error, but if the error is too low, the power is not enough to turn the robot. Therefore, there is a conditional integration so that the controller make the final adjustments to perfect turning. The main algorithm that we have implemented in our robot is a left wall following algorithm. It basically follows the left wall until it reaches the exit. As you can see from the left image, ideally we would expect the robot to turn exactly 90 degrees, right, when it receives the turn right command. But in real life, there could be some errors, but we want to double check the angle so that we could adjust it slowly and more precisely. We have 3 different front movements. The first one is used in most cases when the robot is between the walls. It tries to keep the distances between left and right as well as have a steady orientation while moving forwards. The other 2 are used when encountered with turns. Let's talk from the example that we have. The front is blocked and left is blocked. The robot realizes that the right is open, so it stops and starts move middle function. Likewise, it goes to the center of the road on the right, and when it reaches there, it stops one more time. Afterwards, the robot turns, in our scenario, 90 degrees to the right, and then initiates the move forward to between walls function to get the robot back to the between walls. All 3 of these movements use a PD controller.
This part of the algorithm development is still in process. The goal here is that while the robot navigates in the first round, it creates itself a map to find the shortest path afterwards and follow the shorter path in the second round. Currently, the robot is capable of mapping the pathway. Nonetheless, it does not yet find and implement the shorter path. So to sum up, our code is basically doing the following in a loop. If the path is clear, it moves forward. If the left wall is distant, it turns left. If none of these hold and there is an obstacle ahead, the robot stops and turns.
In conclusion, the Maze Runner project has been a valuable experience in mechanical engineering and robotics. We successfully designed a robot capable of navigating a maze autonomously while achieving our goals of efficiency, compactness, and minimal collisions. During the project, we discovered how crucial it is to combine hardware and software properly. Using a closed-loop control system really helped improve our robot's performance. As we look ahead, we want to highlight two potential improvements for our robot. First, we need to re-evaluate our design for navigating uneven terrains. Enhancing the robot's ability to adapt road cracks and rough surfaces can significantly boost its reliability. Currently, we are actively developing better mapping techniques for maze navigation. By focusing on fixed fall distances and defined entrance and exit locations, so during our project, we got help from certain people, who is Çağatay Başdoğan, our professor, Ömer, Yiğit, Feras, Kiki, Mehmet, Akif, Türk geldi, Selim Ölçer, and Burhan Karahasan. So we wanted to thank all of them.